How are we doing out there? Can you see my screen? Hopefully you can. We are going to start out and talk about some extra integration technique problems as we enjoy this wonderful snow day. All right, these are the problems that we didn't finish yesterday, and we're going to finish them today. So have your packets ready from the section on partial fractions, and here we go. We got problem number 6. This is the integral of 3x to the fourth plus 1 over x squared minus 1 dx. If you remember from yesterday, the idea was we can use partial fractions as long as we know that we've got a proper fraction, but this is not proper. So the technique we're going to have to use is a long division right up here. So what we're going to do is we'll divide x squared minus 1 into 3x to the fourth plus 1. And you see that I wrote that out as 3x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1. So here's the whole process. We take x squared and we divide it into 3x to the fourth, and we get that to come out as 3x squared. We take the 3x squared, multiply by the x squared minus 1, and we get minus 3x to the fourth, and then a plus 3x squared when we subtract everything and multiply this through. So 3x squared times x squared is 3x to the fourth. Negative 1 times 3x squared is 3x squared. Change your signs. All right, so we add, and we end up with a 3x squared, and then carry down the 1. And then we say, how many times does x squared go into 3x squared? Well, that's 3 times. 3 times x squared is 3x squared. 3 times negative 1 is a negative 3. Change your signs. 1 plus 3 gives us a remainder of 4. So we're left with a 4 over x squared minus 1, since we put the remainder over our divisor here. Okay, so if you remember, now we've got a couple little parts here, a couple terms, and then we've got this 4 over x squared minus 1. What do we do with that? Well, we're going to need to decompose that fraction. So 4 over x squared minus 1, the denominator factors into an x minus 1 and an x plus 1. So this becomes an a over x minus 1 plus b over x plus 1. If you remember from class, what we need to do is combine the two fractions and compare the numerators. So a times x plus 1 plus b times x minus 1 has to be equal to 4. So our numerators will be equal. We choose our zeros here. X equals negative 1. When we plug that in, we end up with a negative 2b is equal to 4. So b is equal to negative 2. And then I can plug in x equal to 1, and I get 2a is equal to 4. So a is equal to 2. Altogether, that means we can decompose 4 over x squared minus 1 into 2 over x minus 1, replacing the a, minus 2 over x plus 1, replacing the b. So let's put it all together. What we're now integrating, instead of 3x to the fourth plus 1 over x squared minus 1, we have rewritten that as 3x squared plus 3 plus 4 over x squared minus 1. When I integrate the 3x squared plus 3, that becomes an x cubed plus 3x. Plus the integral of 2 over x minus 1 minus 2 over x plus 1 dx. The first part integrates to 2 natural log of absolute value of x minus 1. Second part to minus 2 natural log of absolute value of x plus 1 plus c. So altogether, we get this statement right here. And remember, we can combine this into one logarithm. And the way we do that is we bring our coefficients in as exponents. So we're left with a natural log of absolute value of x minus 1 squared divided by the natural log of x divided by x plus 1 squared. All right, that's because this 2 moves in as a exponent on the inside. And because we subtract the two logarithms, we divide their inputs. So altogether, our answer is x cubed plus 3x plus natural log of the absolute value of x minus 1 squared over x plus 1 squared plus c. And remember, you can pause the video at any time if you need to go back. That's why I'm doing this. Number 7, the integral of x plus 2 over x squared plus 5x dx. Right? In this case, we need to do partial fractions because we see that we can factor out our denominator. And so we're going to break this up into two fractions, a over x plus b over x plus 5. And we need to figure out what a and b are. So using our giraffe math, all right, and combining this, we get a times x plus 5 plus bx has to equal that numerator of x plus 2. What x's do you choose to find a and b? Well, choose x equals to 0. When we do that, the b term goes away, so we're left with a 5a which has to equal to 0 plus 2, which is just 2. So 5a is equal to 2, and a is 2/5. The other one I want to try is x equals -5. When I plug that in, I get just a -5b, which equals to -5 plus 2, which is -3. So b is equal to 3/5. In other words, we can decompose this fraction into 2/5 dx over x plus 3/5 dx over x plus 5. When we evaluate those two integrals, we get a 2/5 times natural log of absolute value of x plus a 3/5 natural log of absolute value of x plus 5 plus c. Combining these two, we're adding the two logarithms, so we're going to multiply their inputs, and then also we'll move in their coefficients as exponents. So we're left with a natural log of absolute value of x to the 2/5 times x plus 5 to the 3/5 plus c. Number 8, very similar problem. We got the integral of 2 dx over x times x minus 2. Over off to the side, I've decomposed that into a over x plus b over x minus 2. We combine this to get a times x minus 2 plus bx, which has to equal 2. The two numbers I want to test are x equals 0. When I do that, I get a 2b equals 2. I don't know what's going on there. I switched the order of them. That's what went on. So this should be x equals 2 is what I plug in here. So 2b is equal to 2 and b is equal to 1. When I plug in 0, that's what this should say here. Sorry, I can't correct that. I get -2a is equal to 2 and a equals -1. You get the same answer. Sorry about that, but these two x's are switched. All right, so when I decompose that, I get a -1 over x dx, and I get a 1 dx over x minus 2. This first integral comes to negative natural log of absolute value of x plus the natural log of absolute value of x minus 2 plus c. And since we subtract the natural log of absolute value of x, when we combine these two fractions, that x will go to the denominator of the input. So we get natural log of absolute value of x minus 2 over x plus c. All right, number 9, this one's a little bit different. We have something that's not proper. The integral of x squared plus 6x minus 10 over x squared minus 3x minus 4. Now, you can use long division on this. That's perfectly fine. But I want to show you another trick that you can use when you have the same degree in your numerator and denominator. And that's to write this as two separate fractions. One part of the fraction we're going to write as the denominator over the denominator. So in other words, x squared minus 3x minus 4 over x squared minus 3x minus 4. And then the second fraction, we need to figure out how we can add the two numerators up to get to x squared plus 6x minus 10, which is the numerator that we want. Okay, so in other words, I need to add x squared minus 3x minus 4 plus something to get x squared plus 6x minus 10. Well, notice if I add a 9x, that'll get me negative 3x plus 9x to 6x. And if I add a -6, that'll give me a -4 plus -6 equals -10. So my second fraction will be 9x minus 6 over x squared minus 3x minus 4. Another way of looking at that, I'm just subtracting the denominator minus the numerator, which gives me a 9x minus 6. So now I've got two fractions here. Why would I ever do it like this? Well, this first fraction divides to 1. That's going to be easy to integrate. And the second fraction is a proper fraction that we're then going to be able to do integration by partial fractions on. So I set it up. The denominator factors to x minus 4 and then x plus 1. So a times x plus 1 plus b times x minus 4 is equal to 9x minus 6. I try -1. I get a -5b equals -15. So b is 3. And then I get an x equals 4 as my other try here. And I get a 5a is equal to 30 and a is equal to 6. So in other words, I get a 6 over x minus 4 plus 3 over x plus 1. So as you can see, when I decompose it, all right, I get the integral of dx. That's the first part, the x squared minus 3x minus 4 over itself. And then I've decomposed the other part to 6dx over x minus 4 and a 3dx over x plus 1. When I integrate dx, I get an x. When I integrate the other two parts, I get a 6 natural log of absolute value of x minus 4 plus 3 natural log of absolute value of x plus 1 plus c. Okay, another situation where our fraction is not proper, an x cubed minus 11x minus 15 over x squared minus 2x minus 8 dx. So this is number 10. So I go through and I do my long division. I'm not going to go through every detail here, but basically when we want to see x squared go into x cubed, that's x times, multiply the x through and subtract. And we had to figure out how x squared goes into 2x squared minus 3x minus 15. Well, that's 2 times. Take the 2, multiply it by the divisor, and subtract, and we end up with an x plus 1. And that is going to be our remainder, which we put over this x squared minus 2x minus 8. You'll notice this last part, just like the previous problem, we can break up into partial fractions. The factors on the bottom being an x minus 4 and an x plus 2. Okay. When I combine them back, I get an a times x plus 2 plus b times x minus 4 has to be x plus 1. I try negative 2 and 4. You've seen a lot of this at this point, so I'm not going to go into too much detail, but you get b is equal to 1/6 and a is equal to 5/6. So here is our two integrals that we want to integrate. The integral of 5/6 over x minus 4 dx and the integral of 1/6 over x plus 2. And whoops, hopefully you caught my mistake. There should be a dx there. All right, so now I want to integrate the x plus 2 part. Remember, that was the very first part before I did the partial fractions. And then I've got my fraction part, which is these two integrals, 5/6 over x minus 4 and 1/6 over x plus 2. And I get my final answer is x squared over 2 plus 2x plus 5/6 natural log of absolute value of x minus 4 plus 1/6 natural log of absolute value of x plus 2 plus c. Okay, the next three problems are going to all involve what happens when we have limits. So unlike substitution, we're not going to change our limits at all because there's no substitution going on, but there's a little trick that you're going to need to know in order to evaluate these definite integrals. So the first things first, this is a partial fraction problem. So we need to make sure that we find out how we can break this up, decompose it. So I'm going to decompose it into a over x plus 5 plus b over x plus 1. We need to figure out what a and b values will make a times x plus 1 plus b times x plus 5 equal to 1. If I choose x equals -1, that makes b equal to 1/4, and x equals -5 makes a equal to -1/4. So we're left with the integral from 0 to 1 of the -1/4 over x plus 5 dx, plus the integral from 0 to 1 of 1/4 dx over x plus 1. When we integrate, just like before, we get -1/4 natural log of absolute value of x plus 5, plus 1/4 natural log of the absolute value of x plus 1. If I pull out a 1/4, and then I notice that I have a negative here, which will throw this x plus 5 into the denominator, this will simplify into 1/4 natural log of absolute value of x plus 1 over x plus 5, which we want to evaluate from 0 to 1. So this is going to be easier if you combine your fraction and your natural logs first, rather than plug in from the very start. Not only easier, it's going to be the correct way to do it because you're not going to be able to do it other ways in some cases. So combine first. Now, once I combine, I'm going to plug in 1 and I'm going to subtract when I plug in 0. So when I plug in 1, I get the 1/4 natural log of 2 over 6 or 1/3 minus 1/4 natural log of 1/5 when I plug in the 0. Notice that I've got two natural logs that I can combine. I'm subtracting. So natural log of 2/6 divided by 1/5 will get 2/6 times 5. And this reduces to 1/4 natural log of 5/3. All right, so remember your log rules. Subtraction means that we divide by the inputs. Number 12, the integral from 0 to 2 of 3 dx over 4x plus 1 times x plus 1. So decompose it just like before. We want a plus 4x plus 1 plus b over x plus 1 has to equal the original. That'll mean that a times x plus 1 plus b times 4x plus 1 is equal to 3. I test -1 and -1/4 and end up with b equal to -1 and a equal to 4. So our two new integrals are the integral from 0 to 2 of 4 dx over 4x plus 1 minus the integral from 0 to 2 of 1 dx over x plus 1. So now we want to integrate these. The first one becomes the antiderivative natural log of absolute value of 4x plus 1 So you might ask yourself, where did the 4 go? Well, technically what we're doing is when we integrate this, it's 4 times the natural log of absolute value of 4x plus 1, then divide by the 4 that we get from the chain rule. It's a reverse chain rule or substitution. Well, a 4 divided by 4 would just be 1. So there's a 1 invisible coefficient here. Another way of looking at it, if I were to take the derivative of this, that would be a 4 natural log of absolute value of 4x over 4x plus 1, which it matches here. So there's no extra thing we need to put out front. All this is minus the natural log of absolute value of x plus 1. So remember the trick. You want to combine your two natural logs before you go forward. So this becomes a natural log of the absolute value of 4x plus 1 over x plus 1 with a 0 and a 2. I'm going to plug in the 2 first. I get a natural log of 9 over 3, which is 3, minus the natural log of 1 over 1, which is 1. So this becomes natural log of 3 minus natural log of 1. Since natural log of 1 is 0, that's just natural log of 3. Last one with the limits here. So we've got the integral from 2 to 3 of 3 dx over x minus 1 plus x times x plus 2. I'm not going to go through all the details. If you want to write this down, here's the decomposition right here. A ends up being 1, so it's 1 over x minus 1. And b is negative 1, so it's negative 1 over x plus 2. So those are our two integrals right there. The light bit makes a nice little appearance right here. Say hello. That's just me messing up. So when we find the antiderivative, we get natural log of absolute value of x minus 1 minus the natural log of absolute value of x plus 2. The little zoom window hides it, but basically this is the integral from 2 to 3. Combine first so that it's easier to plug in. So I get a natural log of 3 minus 1 over 3 plus 2, which is natural log of 2/5, minus the natural log of what we get when we plug in 2, which is 1/4. When we combine our fractions, in this case, combine our logarithms with subtraction, we get natural log of 2/5 divided by 1/4, which is natural log of 8/5. All right, our last two problems right here, if I can get this going, there we go, is the integral of 8 dx over x squared minus 10x plus 26. This is problem 14. Now, if you look at that, it's not anything to factor this denominator here. How do you do it? You're not going to factor it with integers or any other easy to factor issues. So what do? Well, one technique that's possible is the technique of completing the square. So how do you go about doing that? So just a little reminder, completing the square is the process that we use, all right, whereby we divide our linear coefficient by 2 and square it and add that to our quadratic, and that'll make it into this nice square. So what do I mean by that? So if you look at the first two terms here, x squared minus 10x, we ask ourselves, what can we add to that to make it a square? So what we do is we take our negative 10 and divide it by 2, so that's negative 5, and square it. When we do that, we get negative 5 squared, which is 25. So in other words, this statement, if we completed the square, was x squared minus 10x plus 25. The problem is the original had an extra 20 and at a 26, all right, not a 25. So if we add an extra plus 1 here, we get the same statement as before, x squared minus 10x plus 25 plus 1. Well, why would we ever do that? Well, because the first three terms are just x minus 5 squared, and then with plus a 1. So I'm going to rewrite my denominator as 1 plus x minus 5 squared. So now I'm integrating 8 dx plus over 1 plus x minus 5 squared. Does that look familiar at all? When we have an over 1 plus something squared, that antiderivative is an inverse tangent. And there's a little baby substitution in there. So in other words, this integral, the antiderivative ends up being 8 inverse tangent of x minus 5 plus c. So the completing the square got it into a form that allowed us to use inverse tangent as our antiderivative. The last one here, number 15, uses a very similar process. The integral of dx over the square root of negative x squared minus 4x minus 3. So what you may notice is that square root with an x squared maybe gets you to think about inverse sine, all right? And in fact, that's what this is. So let me show you how we would complete the square in this one to get that. So we have a negative x squared minus 4x minus 3. If I take out a negative, I get a negative x squared plus 4x plus 3. On the inside, I look at my linear coefficient and I say, how can I complete the square to make this work? I divide this linear term 4 by 2 and square it, and I get a plus 4. So in other words, x squared plus 4x plus 4 is a square. It's x plus 2 squared. Okay. The problem is it doesn't quite match what I had originally. I had a plus 3, not a plus 4. But how can I account for that? Well, I write this as x squared plus 4x plus 4 minus 1, which is also x plus 2 squared minus 1. So notice everything had a negative out front. So what I can do is distribute my negative, and I get a 1 minus x plus 2 squared. This is another way of rewriting or writing negative x squared minus 4x minus 3. When I rewrite my denominator with this new form, it's the integral of dx over the square root of 1 minus x plus 2 squared, which is perfectly fitting our inverse sine antiderivative. So this is the inverse sine of the input x plus 2 plus c. So we cracked the code on that one. This doesn't always work, but this is a new thing on AP, and they want you to know how to do it. Okay, so in our remaining time, what I want to do is I want to show you what your homework is, which is the help session number 19. And this can be a little tricky when you first go out doing this because we've learned 3 different techniques for finding antiderivatives, and it's hard to know sometimes which technique to use when. So let me give you a little bit of an idea. Our 3 techniques we've used are substitution, integration by parts, and integration by partial fractions. Substitution you want to use whenever you see an inside function or you see a function whose derivative is somewhere in the integral. Okay. Where do we see ones that substitution might work on? Well, right away, I see number 1. I have a square root and something inside the square root. Not only that, the derivative of x to the 4th involves x cubed. So substitution is a good start for number 1. Number 2 also would be a good one for substitution since I have a cosine of tangent of x. There's an inside function in there. Not only that, tangent of x's derivative is secant squared of x. So substitution would be nice there. I'm not going to show you all of them, but there are others in here that would involve a substitution. Our next technique, integration by parts. Okay, when might you use integration by parts? When you've got 2 different types of functions, like a logarithm, or you've got a sine function, exponential, polynomials that are multiplied together. That's integration by parts. So do we spot any that are like that? Number 9 is a perfect example. I've got a polynomial, x squared, and I've got e to the negative 3x. Right, so integration by parts, or even tabular, if you're brave, might be a good idea for number 9. Don't forget that things like number 13, inverse cosine of x, are also good candidates because at the top of the Lipit stage, you've got logarithms and you've got inverse trig. All right, and we showed how we can do integration by parts using those. The last one we did is integration by partial fractions. How do you know when to use that? If you have a rational function, a fraction, okay? And in particular, if you've got a situation where you can factor the fraction into separate parts. So like number 5, a good candidate for that. Number 12 is a good candidate for that because we can factor our denominators there. The gold level, I've mixed in a couple of ones where you might have to use other techniques like long division, maybe what we just did with completing the square. So be thinking about those. Those are the extra ones here. All right. So good luck. The help session is a nice set of problems that will get you to thinking about what you really need to do. All right. It's been great. Have a fun snow day.